already mentioned that there's a rich variety of substructures and protoplanetary disks, so I think I'll just skip ahead since I missed some time. In the north, we have an opportunity to target about 30% more of the Herbig sample and to image some disks that have never been imaged before. So we set out to image the disks around PDS 201, PDS 178, which is a known binary with about a 1 to 2 arcsecond separation. So this would be a good candidate for companion-driven spiral arms. And also HD 56895, which is another single star. And we obtained the first images of one of these disks. So for our mini survey of about 3 targets, we have a detection rate of about 30%, which I think is pretty good for a blind survey of protoplanetary disks. So this is the PDS 201 system. This is about a 2 solar mass star in Orion at about 340 parsecs. Somewhat interestingly, Gaia DR1 misplaced the system at about 160 parsecs, which caused it to end up in our list of systems within 200 parsecs. So I'm not sure what caused this discrepancy, but I can't say that I'm disappointed by it because it ended up in this surprising discovery of actually a remarkably large protoplanetary disk. So this disk around PDS 201 extends to 250 AU. This is on the upper size of protoplanetary disks, and this is honestly the only reason we were able to obtain these images of it is because of its quite large size. The disk also has a pretty large gap extending to about 140 AU. This image on the left shows the same images that I was just showing you in a tricolor scheme. So here you can see the fainter features of the disk also, including the near side backscattering surface and the far side forward scattering surface. You can see the system's SED in the top right and our best fit model to it, and also the best fit model disk image corresponding to this model in the bottom right, and also its injection in the data in the middle. The 140 AU size of the gap is well supported both by these images and by the dip in the mid-IR SED at about 10 microns. So this is also a pretty large gap, and we think this might also be caused by a pretty massive planetary system, something possibly like an HR 8799. Although given the system's distance and the disk's inclination, these planets might be pretty challenging to detect and might require something like infrared interferometry or possibly imaging with ELTs in the future. So I also want to briefly mention a system that we specifically targeted due to its substructures. So this is a disk that had been imaged before. This is MWC 758, and you can see it in polarized near-infrared scattered light on the left from Benessi et al. 2015. This disk has a remarkable pair of 2 spiral arms that are pretty symmetric with respect to one another. And this disk has no known stellar companions and is not thought to be massive enough to be gravitationally unstable. So it's a good candidate for planetary-driven spiral arms. And we went and re-observed this system in the thermal infrared with the LBTI from about 4 to 5 microns. And we detected what looks to be a point source near the end of the southern spiral arm. This point source has several features that are consistent with the planetary explanation, such as it has no counterpart in the polarized light. It has a red mid-infrared color, and it's at the correct location to be matched up with the spiral rotation pattern speed from Wren et al. 2018. And I think this has been slightly revised as of this year, but it's still consistent with the new spiral pattern rotation speed numbers. I wouldn't say that we're confident yet in the planetary interpretation of this feature. It could also be a disk feature, or an extension of the spiral arm, in other words. So we're following this up with AILs on the LBTI in order to investigate the object's 3 to 5 micron spectrum. And also we obtained science demonstration observations of this system with NIR. Now, we weren't actually sure what the 10 micron flux of this object is. I can say it's not on the brighter end of our estimates because we didn't obtain this nice booming detection like this simulation on the right here. But I'd say that these data sets are both still undergoing analysis, and we're going to combine this with SkexAO/Keras data from 1 to 2 microns to be able to provide a comprehensive analysis of this candidate from 1 to 10 microns. So I just want to briefly mention a third science case that we've been utilizing the LBTI for. So we've also been imaging systems with known companions in order to push down the mass detection limits in these systems, and also, of course, to search for additional companions. So these are 2 images in the thermal infrared and the L band of 2 young brown dwarfs. Obviously, we didn't detect any new companions. We did successfully push the mass detection limits down. And also, these images enable additional science, such as atmospheric modeling and orbital monitoring. And these capabilities are possible for essentially any of the directly imaged planetary systems in the Northern Hemisphere with the LBTI. So to summarize, the LBTI is a powerful machine for imaging young and forming planetary systems. It'll be described in some upcoming talks this week that I encourage you to attend. In this talk, I've told you about some of our observational studies of planet formation with the LBTI, including the first images of the disk around PDS 201, which ended up being a remarkably large disk with a pretty large gap. I also told you about the detection of a candidate planet around MWC 758, which is consistent with some of the expectations of the suspected planet, although I have to caution that we are definitely not confident in that interpretation yet, and this needs to continue to be followed up. I also showed you some possibilities for other exoplanet system science with the LBTI. We get pretty deep mass detection limits in the L band, typically down to a couple Jupiter masses or so. And it's a good system for reobserving known companions in order to provide in-depth studies of these systems. I didn't mention this last point here, but we're also upgrading the LBTI to become a more powerful machine in the mid-infrared, also specifically at about 10 microns. We're utilizing some of the lessons of the NEAR campaign and trying to implement these on the LBTI to, well, to make it possible to have some of the same sensitivity in the northern hemisphere as now we have in the southern hemisphere with NEAR. And if you're interested in that, I encourage you to look at my poster or to find me and talk to me on Slack. So thanks for your attention.
Great, thank you, Kevin. Since we lost you for a couple minutes, we do have a couple minutes for questions, but I'm not seeing anything on the Slack channel yet. So here's a question from me. I'm really curious about this PDS 201, and maybe I missed it, but how old is this system?
So the age of any individual system is fairly uncertain. So in the literature, this one has estimates ranging from about 1 to 6.5 mega years. It's fairly young as a member of Orion.
But do you think that's a primordial disk or a debris disk?
I believe it's so I'd consider it a protoplanetary disk due to its fractional luminosity and the age of the system.